One is because I think I saw you the other day there. Right. I think, yeah. Not sure. I did get that from the first time. Maybe it just reinforces. Yeah. Just the one.
All right, let's wait for a few more minutes.
Zero.
I got it just for you. I'll get it for you next time.
Yeah, I checked you last time. How's your weekend?
Huh?
How's your weekend?
It's good. About yours?
I think this thing.
I know. You know, I even brought this today. Yes, I didn't need it. AC6, fewer people here, a lot more pleasant.
Life's good.
Yeah. Where you want to put things. Let's wait for one more minute. Okay, good friends. How was your weekend? All right. AC's fixed. Life is good. Let us. Well, the market's down, but you know, as long as you have cash, there's nothing to worry about, unless you don't. So let's get started today. How many of you have started homework 1? Let me ask it this way, so it's more possible. All right. So just make sure. So after today's lecture, live transcription. After today's lecture, you'll be able to finish homework 1 for sure. Yeah. So today we're gonna start with a bit of a review. Oh, by the way, whoever on Zoom that requested live transcription, are you able to see this? The closed captions. I think you're muted. Oh, my computer's muted, but this thing is. Okay, cool. All right. Okay, so last time we talked about, we did some Bitcoin review, which is, y'all are Bitcoin experts by now. So we also did a bit of intro into Ethereum. So we talked about how Ethereum is fundamentally built, it's built different, right, compared to Bitcoin. So Bitcoin, we have UTXOs to track balances and whatnot. Ethereum, there are no UTXOs. We have the concept of an account. Who here remembers how that works?
I guess the Ethereum blockchain keeps an account of how much tokens are on each address.
Right, and it keeps track of it explicitly, right? It explicitly writes out your balance is how much, right? Whereas in Bitcoin, it's kind of your balance is calculated from all of the UTXOs that are related to you, right? It does a bunch of addition and subtraction, and eventually, if you have any leftovers, that'll be your balance, right? But in Ethereum, it's just a number, okay? So that's the main difference. We also talked about two different types of accounts, right? The first one called an EOA, so externally owned account. That's basically all the accounts that have private keys to them. So basically all human created accounts, okay? As opposed to contract accounts, okay? So contract accounts are basically smart contracts. Now, what are smart contracts? Smart contracts are programs that run on the Ethereum blockchain. Right, and this is another key difference compared to Bitcoin. For Bitcoin, all you can do, can I make this go away? I can't, because I don't see it on my screen. Wait. No, it doesn't go away. Maybe you click OK. OK over where? On the tablet. Oh, you're right. Nice. Oh my God. Technology wizard. Okay, so accounts, contract accounts, right? Smart contracts. In Bitcoin, all you were able to do was to use Bitcoin script, right? You can only execute very simple logic in there. The main purpose of Bitcoin script is mainly to verify if it's really you that's able to unlock this UTXO. Right, that's about all the logic Bitcoin has. Well, there's more like I'm actually not sure if Bitcoin has multi-sig, but that's like some very basic functionality. Whereas in Ethereum, there is an entire programming language. There are several actually. The most popular one is the one that we're going to learn called Solidity. There's also a second one that's less popular, but apparently written by Vitalik Buterin, which is the skinny Russian guy that co-created Ethereum. It's called Viper, is the language that he created. But it's not as popular, meaning that if you thought Solidity doesn't have enough community support, just wait until you see Viper. There's like nothing you can find online. So yeah, one of the reasons we're learning a popular language is that even though it's popular in terms of in the context of blockchain, it's still a very new language, right? So we're going to need all the help that we can get. Whereas for Viper, there's no like later on when it comes to deploying, testing, there's limited resources when it comes to what to use and how to use them, right? Because
isn't like Move becoming like popular too, like Sui and Aptos and like a lot of these like new ones being developed? Like
I have no idea.
It's like a new one. But
I actually have no idea. I'll have to look into that. You can maybe email me a link so I can look into it.
As you also see on DeFi Llama, what protocols are using what languages by popularity. So
And other blockchains, some other blockchains like Solana or Near, they use something called Rust, which is another pretty old school server-side language that people used to use to write web servers, right? So now they are repurposing it into writing blockchain stuff. But we're not going to talk about it, right? So we're just going to stick with Solidity for this class. Anyhow, so Ethereum versus Bitcoin. balance is kept explicitly, plus you're able to write programs that run on the blockchain, right? Two main differences. So when it comes to contract accounts, right? For externally owned accounts, the way that we get the public address is pretty simple. We just derive it from the private key. It's mostly the same process as how Bitcoin does it, right? And there are four different fields in an account, right? There's the let's go back. There's the nonce, there's a balance, there's a contract code, and there's storage. All right. So for a human-owned account, the contract code and storage fields are empty because for humans operating it, right? Humans have no logic to begin with, but there's no logic in human-owned accounts, all right? Because we will be the ones operating them, right? We don't need any kind of logic built into it to kind of more or less operate itself. Whereas for contract accounts, right, the address, because it doesn't have a private key, all right, because fundamentally the programs, smart contracts on Ethereum are not controlled by anyone, right? So they don't have a private key, then how do they get their address? Well, the address is the, again, this word I can't pronounce, 256 hash of both the address and the nonce of its deployer. So in a sense, contract accounts, the address of contract accounts are actually somewhat predictable if you think about it. Like if you know what my public address is, and you know what my nonce is, and you know that I'm about to deploy, you actually you can know beforehand what the address of that contract will be. Okay. And again, it does not have a private key. Okay. So basically, if you have a program that just takes in two numbers and then returns the sum of the number, and then you have someone sending a 10 ETH by accident, well, I'm sorry, well, that 10 ETH is forever lost, because unless you already have some kind of withdrawal mechanism built in, which by default it doesn't, the contract account doesn't have a private key. So you can't pull that money out, right? That's it. There's actually someone on Reddit, of course, it must be true if it's on Reddit, again, right? This person, so he was trying to, they were trying to, if any of you guys have heard of WETH, so wrapped ETH. So basically, we're going to get into it later, but ETH, it's a bit different from all the other DeFi shitcoins out there, right? Not only because it's native, but also because all of the tokens that are built on top of the Ethereum network it's kind of like, let's say, for example, the USDC coin, right? The stable coin. If you guys have heard of it, it's run by Circle. It's a stable coin, 1-to-1 to the US dollar, right? So that token is actually managed by a smart contract. USDC is a smart contract, all right? All of your money, like in USDC or USDT, they're just numbers in a program, right? But they're programs written in Solidity that are deployed on Ethereum, whereas Ether is a native currency. It's directly built into a network. So sometimes, let's say you want to swap your Ethereum to I don't know, to buy some Shiba Inu, not financial advice. Okay. If you want to do that, sometimes it's easier to deal with wrapped ETH. So what wrapped ETH does is basically there's a smart contract out there, just like USDC, just like whatever. It's able to, when you transfer ETH into it, it detects it, and then it mints the appropriate amount of wrapped ETH, and then it sends it back to you, right? So it's a one-to-one thing, but all it does is to wrap it inside of a token standard, so it enables more functionality. Okay, so what this person did was that so the way that you get wrapped ETH is by directly sending Ether to that smart contract. Okay, because there's nothing else you can do with Ether. You can only send it. It's just like Bitcoin in a way. When on the user level, of course, in implementation we know it's a number, not UTXO, right? But when we're using it, there's nothing more you can do to ETH other than using it as currency, just sending it to someone. Okay, so this person, okay, he sent Ether to the wrapped ETH smart contract, got some wrapped ETH back, I think he spent, I think they sent over like 50 ETH or something. And it was last year, so it was worth a lot more, okay? So they sent over 50 and then they got the wrap ETH back and they did whatever they wanted to do with the farming or staking, whatever, I don't know what they did. But after they were done, they wanted to turn wrap ETH back into regular ETH, okay? Now they thought, well, you know, the way I got wrapped ETH is by just sending this to that address. Then the way I get it back must be the same, must be also just sending it over there and I'll get regular ETH back. So that's exactly what that person did. And guess what? His 50 ETH, they were lost. Why? Because smart contracts, they have very specific, so he was actually supposed to call a function. Basically, think of it as this. Let's say you're leaving a package at someone's, you're trying to deliver a package to someone. The proper way to do it is actually ring that person's gate, whatever, and then if they let you in, then you can put the package inside the gate. But what that person did was just like any other FedEx person, right? Just threw the package on the curb and left. But guess what happened? The recipient never got it, right? As far as they're concerned, as long as the package wasn't inside the gate, he never rang the bell, then they didn't know it was there, right? It wasn't accounted for. So sure, their WETH is now inside of that smart contract. It's like, but the problem is, because that smart contract didn't get notified, they kind of, like, he wasn't able to get his regular ETH back. Now, can someone just from that, can the smart contract owner just, you know, take a look at the situation and then, you know, issue him his refund, their refund? I don't know if I keep saying he. Well, no, because smart contracts don't have an owner. Now, later on in the semester, we'll learn that there is a way to establish some kind of ownership control over the contract. But like if a contract is controllable by some random, like, who knows who, right? Then it's not very, you're not building a lot of trust, right? So in order for people to build a lot of trust, the best practice is after you make sure your code is bulletproof, you basically destroy the owner. Not kill the owner, but you assign it to like the zero address. And currently the zero address is kind of like this. So nobody currently holds a private key that can generate the zero address. And in the Ethereum ecosystem, the zero address has turned into a kind of burn address. And a lot of smart contracts ignore the zero address by default because it's supposed to be like a throwaway address to whatever thing that you don't want anymore, you just assign it and throw it to a zero address. So that's what you do to ownership. After everything, you make sure everything works well, is bulletproof, all right? Which means that I'm actually not sure if the WETH contract has an owner or if or whatever, but basically no one was able to help that person, and 55 ETH was lost because of the fact that smart contracts do not have an owner. And you know, once you do something wrong, then you know no one can really save you from that. And this is actually one of the barriers of entry when it comes to Web3 stuff, because traditionally in the real world, right? When we forget our password to our bank account, whatever, we can, you know, someone's able to get it back for us. Whereas in Web3, the beauty of Web3 is simultaneously is one of its biggest downfalls. So the beauty is that you completely control your own money. The only person that can take away your money is whoever else that has your private key. If you don't have a private key, like math literally does not allow anyone else to take it from you. Okay, you've got math backing you up, right? It doesn't matter if you like math or not. Math likes you. Okay. Whereas in our bank account, you know, Uncle Sam can, you know, with a snap of a finger, you know, if I coded Tornado Cash and now just get arrested in a completely different country and then all my assets frozen, right? But in Web3, no one can do that because only you have the power. But if you lose the key to that power, no one can get it back for you, right? So in this system, you are completely in control of everything, but also you are completely responsible for everything. Okay, so we're going a bit off topic, but I think it's something good to talk about. Okay, right. We also talked about how an account nonce worked. Okay, who remembers how it worked? What was the purpose?
It was putting like the header of a block to like adjust the difficulty level.
Account nonce, not the block nonce. Yes.
It basically counts how many transactions you've done, so that basically every time you do a transaction, the counter goes up. And if there's like a transaction that's like still processing, you could like take the counter down and then send another process so that it goes faster than the other one.
So what is it trying to? Why do we have it?
To avoid double spending.
Can you give me an example? Like it could be a scenario, whatever.
Yeah, so like you send like 5 Ethereum to someone.
Yeah.
But like while that's being processed, you send 5 Ethereum to another person, like the network would lose track of that. So that's why there's a counter to say that like one happens after another.
That's one thing. How does it prevent?
This is very like vague, but I remember I think it was like, isn't it like if I'm the sender, it's like 50 or something, and the person I send it to is like 1, and then it.
No.
Oh, okay.
Okay, that's okay. It was the last 2 minutes. Okay, I understand. So I can talk about how this works again. So you were correct in saying that, yes. So your account nonce goes up by 1 every time every time your transaction gets mined. Okay, so let's say it's a fresh account and I've sent money to 2 people, then my account nonce would be 2 at the end of the second transaction. Okay, after the second transaction gets mined. It prevents. So what does it prevent? It prevents the recipient from screwing me over. Okay, so let's say Dylan. Now Dylan's not a snake, but let's assume Dylan is a snake. Okay, I'm sending Dylan 5 ETH, right? But then he sees I have 100 ETH in my account. He's like, wow. How about you give me some of that? And I say no. Well, he's like, well, I have a way to force you to give me your money. So basically, what he could do is basically replay the transaction of me sending him 5 ETH. And every time he does that, because the digital signature is valid, right? It's valid. I signed it. It's just that it was meant for a transaction in the past, right? You're not supposed to reuse it. But then Dylan's reusing it. But with the account nonce, what's great about this is that the account nonce is actually included in the transaction. Okay. So let's say it's a fresh account. I'm sending Dylan 5 ETH. Then the account nonce at the time would be 0, right? In computer science, you start from 0. And so the nonce in that transaction would be 0, right? But then let's say, and then after that transaction gets mined, my account nonce will increase by 1. So now my account nonce is 1. And let's say Dylan tries to pull a quick one, all right? He replays the transaction. But then when the nodes are validating it, they see that the transaction nonce is 0, but my account nonce is 1. So well, that's not right, right? So so that transaction, the nodes would know that transaction is outdated, and it shouldn't be processed again.
Wait, does the nonce increase once you already verify the transaction? I think I'm like kind of confused.
Okay, so every time your transaction gets included into a block, it goes up by 1.
Okay,
So your transactions you initiated,
right,
but further confirmations don't change that.
okay,
So it's just a one-time thing. So basically it counts how many transactions you sent out.
right. But then like last time you talked about the underpriced gas transaction thing.
Yeah.
That stuff.
Yes.
So
Yes.
yeah, so like basically once the person initiates the transaction, usually it get verified unless you pay a very
Yeah,
low
unless you're too cheap. Yeah.
but it get adds to the nonce once you initiate it. Doesn't need to get verified per se. I'm just confused about the
Okay,
order.
so you're confused about how it cancels out like a
Yeah,
stuck
yeah,
transaction, okay. So let's say, again, I'm sending, okay, let's pick someone else. I'm sending Selena 10 ETH, okay? She's also the first person to receive money from me, okay? So the transaction nonce will be 0 in that case, okay? Because my account nonce is 0. I haven't sent money to anyone yet. I sent her 10 ETH, but then I cheaped out on the gas price. So it was underpriced, meaning that I'm not willing to pay the miners enough money. So of course, you know, it's a capitalist world. I love capitalism, right? So people always, you know, miners say, I mean, why does anyone work, right? Besides liking what they do, you work to earn money, right? So and why do people prefer high paying jobs to low paying jobs? Because you get more money. So for miners, their objective is to get more money out of the hardware that they're running, right? So of course they're gonna prioritize the transactions that are willing to pay more, right? And I cheaped out, so you know my transaction is stuck in the mempool for like 10 days or something. So if you send something through MetaMask and then you copy and paste your transaction ID onto etherscan.io, it's like a block explorer, okay? It's actually able to show you an estimate of when your transaction will be included into the next block, when it will be mined, okay? And if you pass in a very high gas price, so gas price versus gas fees we'll talk about later. But let's say when you create a transaction, if you indicated that you're willing to pay a lot of transaction fees, then the miners see that and they want to make money, so they will include your thing right away. But if you say that I'm going to cheap out, then it's going to be at the bottom of the miners list, right? So Etherscan actually shows you an estimate of like when it's going to be included into the next block, and sometimes it could be 10 minutes, 30 minutes, a day, whatever. It depends on how cheap you went. Okay. So let's say my transaction to Selena, it's stuck. It's going to be stuck for 10 days. Okay, but she has to pay rent. So you know I have to give it to her before the end of the month, which is today actually, or tomorrow, which is tomorrow. So 10 days, it's not going to cut it. Okay. So what I can do is I can basically create a second transaction that is exactly the same, besides the amount of transaction fees I'm going to pay, okay? And because the previous one is stuck in the purgatory in mempool, which means it hasn't been processed. And it hasn't been processed, meaning my account nonce hasn't changed because it hasn't been processed. And my money is still in my account because it hasn't been mined yet, right? So what I can do is I can create a second transaction, also sending her 10 ETH, with higher transaction, with higher transaction fee, with the same nonce, okay? So that it will be prioritized. And then the second transaction, because it has a higher transaction fee, right? It will be processed. And then afterwards, my account nonce will become 1, right? Because previously it was 0.
Right.
So for the second, for the second identical transaction that I create, I'm also setting the nonce to 0.
Okay.
Yeah. Because I'm trying to replace it, right? So if the second transaction's nonce is 1, then basically they'll see that my account nonce currently is 0. But this transaction, the nonce is 1, which means there's another transaction before it that hasn't happened yet. So basically the second transaction still won't happen until the first one happens. And even worse, I'll basically be sending her 20 ETH by then.
Right.
Yeah.
So, but then at that time when you send the second one, then the nonce of both it's 1, but then the one can get processed because of the higher gas fee you pay. And then when the person go back to the stuck one, it sees that the nonce is 0.
Yeah,
That's
so
why-
it gets discarded. It's invalid now.
Okay.
So that's how you replace a stuck transaction. Yeah. So in MetaMask, actually internally, it keeps track of your nonce. So you actually have to enable an option to enable you to edit the nonce. So after each transaction, automatically it goes up by 1. You have to actually subtract it by 1.
Okay.
Because you're trying to replace something.
Right. Okay.
You're trying to, yeah.
Can you also like fix mistakes using that?
If only it has been processed.
But it doesn't have to be like the exact same amount, like say.
No, yeah, you can, yeah, I can cancel it by creating a transaction of me sending her 0 ETH. And then, yeah, and a much higher price, so that one goes first.
It's like a language question, like in Bitcoin, nonce was used more for like the solution for the hashing.
Yeah.
And here we use nonce for like countering an account. Is there a reason why? Is there a connection between?
No. Well, Ethereum also has that kind of nonce. It's just in a block. This is specific to an account.
Okay.
Two different nonces.
Yeah, I'm curious about like the origin of the word nonce. Like
It's
why
probably
is it
just
used?
like a throwaway number.
Okay.
The first transaction that's that been encrypted for data basically is gonna be refunded to you.
It's not gonna be refunded. It'll just be like it never happened. Yeah, because it hasn't been processed. All right. Any more questions on that part with the how the nonce works? Don't worry if you have questions. You know, we have plenty of time, especially now that we're actually living in the first world now. Yeah. We have AC now, so you know, I have more patience with when I'm more comfortable. Okay, so moving on, all right. Okay. Yeah, let's talk about Ethereum state. Okay. It is not a region that's occupied by Ethereums. Okay. Ethereum state. So the word state here means the current condition or the current state of things in the system. All right. So in Bitcoin, we already talked about how balance we calculate the balance of an address by aggregating all of the past UTXOs, right? Well, in Ethereum, right, one of the reasons why it didn't use UTXOs and is keeping track of things explicitly is because there's a lot more happens than just monetary transactions, right? In the white paper of Bitcoin, again, it's literally peer-to-peer electronic cash, so it's not meant to do anything more. But Ethereum is meant to be the world computer, it's meant to be the programmable blockchain, right? So things are a lot more complicated. There are a lot more things that Ethereum blockchain needs to keep track of. So they moved away from the UTXO model into the model where your balance is explicitly kept. And the act of explicitly keeping your balance is called keeping a state, right? So because Ethereum keeps the state of things, this is also why in Ethereum you can just look up your balance and it's a number. Bitcoin does not explicitly keep track of the state of things, and that's why when you want to find out your Bitcoin balance, you have to do all the math, right? It does keep track of state inexplicitly because otherwise you won't be able to come up with your balance. But it's not a number that you can just read. Makes sense, right? So the idea is that we have too many things going on, so basically we have to keep track of the most current recent condition of everything, so that when we try to ask for some information, we don't need to do a whole ton of calculation, right? Okay, calculating state. Now, the first one we just talked about, how in Bitcoin it's not explicitly stored, so we have to aggregate all the UTXOs, right? In Ethereum, because your balance is stored as a number, we can just read it from the blockchain, right? It's just reading one number. Okay, so here's the Bitcoin state transition. All right. Now, these are some big CS words, but don't worry. Okay, they're really not. So this is the original state. Okay, this is the original state of. Let's suppose the entirety of the Bitcoin network only consists of 5 UTXOs. Okay, these 5. Right. Oh, okay. Yeah. So here, and now a transaction is being processed. Okay. So what's happening is that we're spending these 2 UTXOs, right? And then we're creating new ones. So basically, it's a transfer of sorts, right? See, the input is 3, the output is 3, right? And apparently they didn't pay for any transaction fees, but that's fine. So just transferring money to someone, okay? So you see how the old UTXOs are getting spent, new ones are they here? No, they're not. So new ones are getting created. And this is the new state after the transaction, right? It's just like the old status of the network versus the new condition status of the network. That's all state means, okay? And in Bitcoin, it's really easy because you're only keeping track of UTXO, so it's just destroying, creating new ones, destroying, creating new ones, right? So it's very, very simple. And the SIG are just signatures used to unlock the UTXOs. Okay. So in Bitcoin, the steps to calculating the next state is that for each input in a transaction, first you have to validate if the UTXOs are being spent is actually valid, meaning that if meaning you have to check as a node, you have to check if the sender actually, if they're able to actually unlock the UTXOs, right? If the UTXOs are like, if they belong to that signer, the sender, okay? And then they verify if the digital signature is valid, right? Basically, using their public address to verify, okay? And when that's done, right? We verify that the sum of all the inputs is no less than the sum of all the outputs. Now that makes sense. You can't just create money out of nowhere unless you're mining, right? When you're mining, the mining rewards, it's literally creating money out of thin air. But aside from that, in a regular transfer, you can't do that, right? So you have to verify that the input is no less than the sum of all the outputs. Right? The output can be less. The extra ones just kind of go to the miner. And then afterwards, all the input ones are deleted, and the output ones are added. That's how UTXOs work, right? Does everyone agree? And is everyone clear on how Bitcoin? This is how more or less a Bitcoin transaction modifies the state of the Bitcoin network. Yeah. So basically, you verify if the inputs are legit. You destroy the input UTXOs. You create output UTXOs, and then you have the state of the network slightly modified, right? Anyone have any questions on this part? No, yeah.
Right, so you also store values of 0.
Oh, they're just like destroyed or they're unspent or yeah. So you can store UTXOs with the amount of with like 0 amount of UTXOs. Some people use that. I don't know if Chaz mentioned it last semester, but some people actually attach notes in like in some portion of the transaction, but they're basically they're sending 0 to someone else, but then they're trying to basically put the notes up there forever. So that's like one way to keep your information on the Bitcoin network forever, but it's also a concern because these aren't going anywhere. Right? People, it's 0, so they're not really going to spend it or anything. It's 0, but it's going to be stuck in the database forever. So that it's actually blows up the network unnecessarily. But again, Bitcoin nowadays transaction fees are pretty high, so no one really uses that kind of thing. Plus now we have Ethereum, we can use smart contracts or whatever to do that. But that's something people used to do, so that's why you can have 0 UTXOs with the amount of money being 0. It's like as long as you're willing to pay the miners a fee to include that, they'll do it, right? You just you can't send negatives, but you can send zeros. If you want to waste money, no one's stopping you from giving me $10 million, aside from the fact that you don't have $10 million. Okay. Maybe you do. Don't tell me. Yeah, you had a question. Someone had a question. No questions. All right. Okay, let's move on to calculating the Ethereum state. Okay. Whoa, yikes, yummers. Right? So the Ethereum state, see, it's a lot more complicated than the Bitcoin state because now we have logic and programs. Wow, it's 21st century, right? So the original state, we start off from this guy owning 1024 ETH, rich man, right? Wow, okay, this is richer. So, but this, look, What's the difference between this one and this one? What do you notice? So remember there's 4 components of an account. We have nonce, we have balance, we have contract code, and contract storage. What does that look like to you?
Contract code.
Yeah, so that's contract code. See, there's if something, then something happens, right? I mean, you don't have to know programming, but basically saying if this condition, then this happens. So that's the logic, that's contract code. This is just data being stored here, so that's contract storage. So we can conclude that this is a smart contract account, and this is an EOA because it's got nothing, right? This one is also a smart contract account. There's logic and there's storage, right? And this one is this one is just an EOA. Okay. Now here, transaction from this guy to this smart contract, right? So when the recipient in the transaction is a smart contract, it's basically an interaction. Okay. So it's the sender that's trying to interact with the smart contract. Okay. Value 10. Now, when you're interacting with a smart contract, besides sending over data, you can also send over money with it, right? It's just that later on when you start to code stuff, realize that contracts need to explicitly state that they accept money. At least in newer versions of the language. Older ones, not so much, and that's why the guy was able to lose their 50 keys, right? So this rich guy is interacting with this smart contract, right? So, and afterwards, what happened, right? Okay, actually, let's walk through what the data does. So if, oh, I get it. Okay, so if 2. So if this slot is 0, then replace this slot with Charlie. That's what it's saying. You don't have to understand it for now. That's not even proper syntax, grammar. That's just pseudocode. Don't worry about it. But afterwards, let's see what happened. This person, the balance decreased by 10 ETH. Why? Because they sent the smart contract 10 ETH, right, in the interaction. Okay. And what happened to the smart contract? Well, balance increased by 10 ETH, right? Because they received 10 ETH. And the storage changed, just like how I said it would, right? Because now, basically, this data here made it so that after running through this logic, the storage was modified. Okay. So this is an Ethereum state transition. And this process happens for every single, this is basically what the nodes are doing, what the miners are doing. When they pull a transaction from the mempool, they go through this process, and then this becomes and then when they get to this state, this one becomes the starting state again, and then they pull another transaction, and they keep doing that until the block is full or whatever, right? So this is how an Ethereum state transition works, and I've got steps. So the first one, you verify the validity of the transaction, right? So the transaction needs to be properly formatted, right? You can't say things like America here, right? It's not a valid address. It's not even hexadecimal, right? So the transaction cannot be malformed. The signature has to be valid. Now this is just like Bitcoin, you gotta check the digital signature, right? The nonce also matches the sender's nonce, right? You gotta check that. And step 2 is to execute the transaction, right? So for the funds transfer, if there is fund transfer involved, you have to check if the person sending it actually has money to do it, right? You can't go negative balance, all right? In fact, in Ethereum, you cannot have negative numbers, right? This is another computer science thing, but Ethereum doesn't have negative numbers. It doesn't have decimals either, all right? So you can't do 1.5, okay? But we're gonna see how we circumvent that in the future, okay? And for the contract call, we then execute the contract code, right? And while we're executing the contract code, maybe storage will be changed, okay? It doesn't have to change, sometimes it does, but usually, okay, so not not all logic needs to change the state. But those that are mined into a block, they do, right? If your logic is read only, meaning that if basically you give me two numbers and I tell you what their sum is, right? That doesn't have to be included into the block for you to know the answer, right? Because it doesn't depend on anything else. Or if you're just trying to read what the variable is, right? You don't need to include it into a block. It doesn't have to be a transaction because you're not changing anything, right? It's almost like when you're in elementary school, there's no reason for a teacher to force you to write something 10 times because it's not changing. Right, so if an execution is successful for the fund transfer, well, the sender gets their balance deducted and the receiver gets their balance increased, right? For the contract call, the storage is updated. So this is how an Ethereum state transition changes. You can see how it happens, and you can see how it's just a tiny bit complicated than Bitcoin. Now there are more things to worry about, right? And imagine if you didn't keep the state of things, right? If I want to know the current storage, and imagine if I want to do that, I have to go ahead and replay all the transactions to get to the current point. That's just like way too much, right? Yeah.
So is there just one global state for everything?
Yes, there's just one global state, despite the fact that we have so many computers on the Ethereum network. It is slow as a snail.
That's sketch.
All right. And the reason why is because there's only one global state. So everyone's basically doing the same work and they have to agree on it, more or less. So you have, let's say 1 million computers all doing 1 + 1 = 2, and then checking with each other if it really is 2, right? So it's not that, they can't work in parallel. They must work on the same things roughly. But every miner includes different, the order that they include transactions into a block also matters, right? But they're roughly the same because they all prioritize the higher fees. Everyone does roughly the same things, and then they have to come to agreement on everything. And this is also why decentralized systems are slow, okay? And this is why it's so difficult to scale. And also why the transaction fees are so high, because the throughput is severely bottlenecked, right? Because again, we have to keep everyone agreeing on everything. That's just slow, right? And it's also expensive because now you have more people, because the supply side is being kept very low, but then now you have more people trying to use it. The demand rises up, so you got higher fees. Okay.
Does the code stay the same while the contract storage is updated?
The code never changes. So the code is the logic. The logic doesn't change, right?
And even with different transaction, it still doesn't change.
What's your question?
Or like even if it's like put in another transaction, the code still the
No. So think of it as this. How many times do you eat a day? 3 times, right? But your stomach stays a stomach, right? Your stomach doesn't become a steak or a burger, right? So the mechanisms someone's really enjoying this. So the mechanisms stay the same, but then what passes through them or what they remember kind of changes up. Yeah.
So just as accounts have thoughts to keep track, and with same thing with the how much Ethereum is in each account, is that like similar system of how the data is stored for the code? Like where is the code actually stored with the address of the contract?
Where is it stored?
Yeah.
So let's go back to all the way to the beginning. See how for every account, there's this bracket thing, and then inside there's balance. There's also like contract code and contract stored in here.
Okay.
Yeah. So every account is their own entity, more or less, contained in that way.
And are all those like already, I guess, is it just once an account is actually made or a contract is created, it just gets added to that list?
Yeah.
Okay.
And by default, everything starts off empty.
Yeah.
And then when you deploy a smart contract into an address, then the appropriate fields get populated.
Okay, thank you.
Is there a limit to how many like transactions you can create per second or something?
There's something called a gas limit for each block. Basically, the max amount of computational power that's allowed to go into each block when it comes to validating and running transactions. There is a limit, but you probably will never hit it. And for your individual transaction, there's also a limit as to how much computation you can do in one go. We will talk about that later, but there is a limit, but you'll likely never hit it. Yeah, and like if you're interacting with a smart contract that constantly hits the gas cap limit, then that's not a useful smart contract. Like no one else can interact with it either because it keeps hitting the cap.
So what's stopping someone from saying just clogging a network with a bunch of like ton of useless transactions?
Oh, people used to do that. It used to be people used to attack Ethereum on that. But the thing is, like when you're doing that, you also have to pay the fees to do it. So you're also losing money. So in a way, you're just like you're trying to spy everyone by wasting your money away on useless
Was
computation.
it like Bitcoin maxis that were doing that?
Well, I mean, if they want to throw money into the system, I don't care. But well, it's more like that's a good analogy. There's nothing stopping you from just right now start screaming in class and then make it so that no one else can hear what I'm talking about. Right now, it's fine. It's just on Zoom. That's a problem. But you won't do that because it's at your own expense, right? Because it's and it's just like how it's not that it's not possible to ruin a blockchain network. Like bigger ones like Ethereum, right? If you 51% attack the network, like sure you can do it, but the amount of resources that it takes, you would earn more if you just play the game legitimately, right? But for smaller blockchains, that's not necessarily the case. For example, Ethereum Classic actually got attacked a couple times last year. Yeah. So it's all about if the economics makes sense to you, if the trade-offs make sense. Now, if you think if you start screaming right now, if it's worth it to you, then you can go ahead and start screaming. But I would think that you don't think it's worth it because your reputation will get ruined. You'll be on the internet forever because it'll go on YouTube. So it's not worth it, right? Yeah. So there's nothing stopping people. So but people have done it in the test nets where money is fake, right? And they're just doing it to screw with other. And like I was actually around for a couple of the attacks. The network was just unusable. Like I was trying to test out my smart contracts on the test network because money is fake, and it would just never get processed. It's so infuriating. And you keep seeing these like garbage transactions from the same address, just doing nothing, like filling up the block over block. Yeah.
Is that why they make you like do a little bit of work from the faucet? Is that supposed to prevent that?
I don't know, but I absolutely hate it that they need you to do it because it never works for me.
The Twitter thing?
First, I hate Twitter. Secondly, like I got my Twitter in 2012. I had less than 10 tweets. I don't intend my 11th tweet to be some like link feed verification.
I forgot about that and someone liked it. I like forgot to delete it.
Yeah,
It's really annoying that you have to do that.
Yeah.
Are all faucets like that?
No. So pro tip. Actually, someone make a Piazza post because I was going to say that Chainlink has faucets where you don't need to post like cringy stuff. But Jordan somehow found a faucet that gave him like 100 test MPs. I don't know how he did it. I don't know where it was. But I was only able to get like 0.1 at the time. He got like 100 from some weird faucet. Well, the problem is like most faucets you find in Google are not working. That's the problem.
Is it because everybody looks up a faucet on Google?
No, it's just
and
that
they use it?
there's one thing, and the other thing is there's no incentive for anyone to maintain it because it's fake money anyways. Why am I spending time and energy into maintaining this faucet, right? So a lot of them are just dead. Like it doesn't. The web page straight up doesn't work. Yeah. All right, any other questions? Yeah. This one?
So under the contract search, what is happening with the 77 state?
Oh, this person started off with 77, ended with 77, because the transaction is not about this person, so nothing happened.
Oh, you would have.
Yeah, this one and these two are not modified, because the transaction happened between these two.
The bottoms were also transactions.
No, so it's okay. These are accounts. So this is like an abbreviation of their address. Not abbreviation, it's just like some random hexadecimal. But these are accounts, okay, 4 accounts, 1 transaction. So that's the state before the transaction, and that's the state after the transaction.
The two do anything to do that?
No. Oh, wait, which one?
The two, Charlie.
Oh, yeah, okay.
That's the third.
So the way 2 works, okay, so if you look at the logic here, right, it's because it's this person interacting with this contract. What this is saying is that, so let me start from here because I can point to this. It's saying that if the storage, if the third storage slot in the contract is 0, then you assign it to Charlie. Then you assign Charlie to it, right? Because so basically tx.data, transaction data at index 0. So computer science, we start counting from 0, right? So index 0 meaning the first item. First item is 2. Okay. So what's at storage index 2? So index 2, again, index 1 is 0, so it's the third item. 1, 2, 3, that's 0. So this if condition is met. So now we go into this logic, right? Because it's 0, so we assign index 1 of the transaction data, which is second item, which is Charlie, into this 0 slot, and that becomes Charlie. Thanks. See a hand, half hand.
Yeah, wait, why is it the third storage again? Why isn't it first 0? Because isn't like in,
You're saying this part?
yeah,
Okay, so tx.data refers to this thing. So you have to, this is kind of like a math equation. You got to start off on like the innermost
yeah.
thing, right? So the innermost thing is transaction.data at index 0, right? Which is 2,
Oh,
right?
okay.
So then whatever inside this outer bracket becomes 2. So it's storage bracket 2. So that'll be the third item, 1, 2, 3, that's 0.
Oh, yeah, got it.
Yeah.
Okay, thanks.
That's programming. This is your first taste of programming, although this looks more like Python than anything else. It's not even Python. It's like half Python, half other stuff. It's not proper language. Okay. Any questions before we move on to block structure? Last call for Ethereum state.
It's kind of a random question, but
Yeah.
like who finds the transactions on the test net? Or just like
Volunteers.
volunteer
Yeah,
miners?
Just bigger organizations who also use the network. It's like, why would no, that's a bad analogy. I guess, like if you're a big enough organization, you just feel like you should give back or whatever. And sometimes why would you donate to charity? I'm kidding. Sometimes I'm not sure, but I think I'm not sure if official Ethereum like dev groups or whatever, I'm not sure if they run their own nodes too. But bigger players like Chainlink or whatever, they chime in by running their own validators and whatever on the testnet. But really running things on the testnet has no real economic incentive, right? It's just that, it's a decent thing to do. Right? It's like 10-year professor. No, I'm not. Okay, any other questions? Right. Okay, let's move on to block structure. Ooh, yikers. What is this? Do not worry. Let's go like row by row. Okay. So the header we have, in the header we have parent hash. Now that's, we all know what a parent is, that's just the previous block, right? That's the parent. Omers hash, what are omers? Now I had to look this word up, actually. O-M-M-E-R. So the second one here, omers hash.
Aren't they kind of like orphans, like Bitcoin, like orphans?
Yes, but in Bitcoin, orphans are thrown away. They are. That's the harsh reality. That's just how things work, okay? But Ethereum is more moral in that sense, right? We have omers, which, if I remember correctly, it's a gender neutral uncle. I don't even know. But
Yeah, exactly.
is it a gender neutral uncle?
Yeah.
What is a gender neutral aunt?
Yeah.
Anyhow, that's not relevant. It's not gender studies. Okay, so we've got. I'll just call it they hash. Okay. Omers hash. Okay, so we have Omer, not uncles. Omers in Ethereum. Okay, so basically it's the same as orphans in Bitcoin. Basically, mined blocks that are mined just a bit too slowly, not fast enough to become the longest chain, but it's still valid. Okay, meaning that this miner did their work, they got the answer. Sadly, they got it maybe 2 seconds too late, right? And when it starts propagating, it's a bit too late, so it gets overtaken by the other one, right? Now, I said orphans in Bitcoin are thrown away, right? They are, because if you have an orphan block, then you don't get anything, right? Too bad, haha, get good, right? But in Ethereum, omers are also rewarded, just not as much. Okay. So like if you did the work, you found the answer just a bit slowly, here's a participation trophy. Okay, so that's what it is. Beneficiary, yeah.
So if they're rewarded, but like their block, their chain is still, like a little shorter, they would they just get rewarded then move on to the.
Actually, I'm not sure. All I know is that they get rewarded.
Okay.
Yeah. That's a good question. Yeah, I'm not too sure. I'll have to think about that. Anyhow, or Dylan can look it up. How uncles or omers get rewarded. Anyhow, and this was back in what? When did Ethereum start up? 2013. They're ahead of the time with the gender stuff. Yeah.
Is there any benefit to the network for reporting the omers?
Feelings are not as hurt. No, I don't know. I'm not sure
I
actually.
feel like it's almost an incentive, right, to make them keep money.
Yeah. So you don't. Yeah. So it's not like strictly what like there's a. I guess yes, it's an incentive.
Would you say that it keeps competition low though? Because if miners are not incentivized to update their hardware, like their mining hardware, they're just like, I'm gonna get paid, so I'll just keep using this old hardware.
No. Okay. So the thing is, the incentive, the urgency to update hardware stems from the time it takes for you as a miner to find the next block. And that's determined by the difficulty, right? And difficulty is dynamically adjusted. It's just like Bitcoin, it's dynamically adjusted by the overall hash power. So the urgency for you to upgrade is actually driven by everyone else.
Okay.
Yeah, so even if you don't if you don't upgrade, you won't even get an Omers award.
Because you won't even be able to.
Yeah, you won't keep up at all. This is just like if you can keep up, but then you're just bad luck. Then you get something. All right. Beneficiary. Right. Beneficiary is just the miner's address. So whoever receives the actually it's not strictly the miner's address because miners can actually decide to give it to someone else. Okay. So that's basically whatever entity that receives the block report. Okay. Now we have state root, receipts root, and transaction root. Okay. What are these? Now these, they're actually now what do they remind you of here? Yeah, they remind you of Merkle trees, and that's kind of what they are, right? These are basically, you can think of them as proofs as to whatever everything that's happened inside of this block, all the changes, right? And the reason why we have 3 of them is because Ethereum is a lot more complicated, as we said, right? Bitcoin only has to keep track of UTXOs and whatnot. So, you know, one Merkle tree is enough. But now we have the account state and we have transactions that can modify state, you know, a lot of things. So these 3, they basically have, they all have different components here, right? So you see by the way, this is also tree. I don't know why it's spelled this way. Tree and tree, anyhow. So you see the world state tree, okay, it's state root. The world state tree. See, every single leaf node is an account state. Okay. And in here, there's also the account storage tree, and that's embedded inside the state tree. Okay. And the receipts tree is just so the receipts tree is actually the let's see. Yeah. The receipts tree is actually the outcome of the transactions. Right? This stores the state changes, if I remember correctly. And the transactions tree just stores it's a summary of all the transactions. You can see what's the transaction nonce, gas price, gas limit, who's the recipient, what's the value, VRS, it's 3 different components of the ECDSA digital signature, data, and then you don't have to worry about that. Okay. So these you don't have to entirely memorize. You just have to know that they exist, okay? They will be on they won't be on the exam because the exam is just programming. But just make sure that you know what they are, okay? These do not, like a lot of the concepts here, they don't directly impact how you write your programs, but it's good to keep them in mind because in the future, when we start talking about, if we have time, we start talking about event logs and how the filterings work, how events work. These might come in handy when you're trying to understand. Okay. Logs bloom. This is used for event filtering, something called the bloom filter. Now, if you're a CS major, you've heard of this. I've heard of it. I did an assignment on it. I forgot what it was. And I'm here today, so you don't have to worry too much about it. Okay. Well, difficulty speaks for itself. Just the block difficulty, right? The number is the block number. All right. Gas limit, gas use. Gas limit is the max amount of computational, basically transaction fee limit that the actually no. Okay, so gas is a bit complicated. I actually don't know if I cover it here. I'll say it now. So in Ethereum, transaction fee is actually the product of 2 numbers. Okay, the first number being gas used. So gas used. How much gas is used is determined by the type of action that you do, like what contract you interact with, or if you're sending someone money. So let's say you're interacting with a smart contract, with the same smart contract. Doesn't matter when you do it and how many times you do it, gas used will be the same for the same code. Okay, it's basically a measurement of the amount of computational power used. The second number in the equation is actually the gas price. So gas price basically indicates how much you're willing to pay for each unit of computation. Okay, so gas used times gas price equals the transaction fee, equals gas fees. Okay, so the gas limit here is the gas use limit, meaning that this is just the cap on the total amount of computation this block should include. Okay, and gas used is how much computation that actually happened. Okay, timestamp, self-explanatory. Extra data is, I don't know what it is actually, it's not important. Mix hash, not too important, you have to nonce. Okay, and the body, it's just it's just like a Bitcoin block. You have a bunch of transactions, and then you have a list of gender neutral uncles. Okay. Any questions on this part? Now, if you're confused about the trees, don't worry too much. We'll come back for it next time. But these are not, like, you just have to know that they exist, and that instead of having one Merkle tree, you have three and four indirectly, but 3 trees directly included three roots of the trees that are directly included into the block. Okay.
So does the gas limit also kind of act like a block size, unless it's only includes so much computation in one block?
So computation, so gas is not only computation but also storage. So there are two ways to use gas. The first one is asking the computer to do something really complicated, but it doesn't have to store a lot of data, but it has to calculate a lot of things. That's one way to use gas. The other way is you can not calculate so much, but you store a bunch of things. So storage is also very expensive. Okay, actually more expensive than calculation, because when you're calculating something, you calculate it once and that's it. But when you're storing it, it's going to blow up the blockchain forever, right? So two different ways that you can result in gas fees. Gas use. Yeah. So it just limits the combination of calculation and also storage.
Okay, that's different than like the block size.
So let's say all the transactions in the block are just computationally heavy, but they don't store anything, right? Then you can blow the gas limit without increasing the storage too much. But if you have a bunch of transactions that are spamming storage but aren't doing anything, like then the block size would be bigger. There's also a block size limit. I forgot what it was, but then in that case you would increase the block size, but then there won't be as much computation.
I guess like function wise, what like makes the world state tree different from like receipts tree? In terms of what they do.
The receipts tree corresponds to the transactions tree. So receipts are specific, like they're transaction receipts. So this one and this one go hand to hand. World state is like something else.
Okay.
World state includes like normal accounts and whatnot. This like each receipt has its own corresponding transaction. Yeah.
Can you explain like the Omer thing again?
That's an Omer. No, so Omer is like let's say we're both miners, all right? And now do you remember what orphans are in Bitcoin?
That's what I was kind of.
Orphan blocks, okay. So orphan blocks in Bitcoin are basically, let's say we're both Bitcoin miners, okay? And you find a block 2 seconds before I do. Okay, now we both found valid blocks. Because you did it earlier, then you would outcompete me, right? Because you finished earlier, you propagate more. Then I would have this block that's valid, but no one else wants to adopt it. So that's an orphan block.
So in Ethereum, they still get rewarded.
Yes, in Bitcoin, orphan blocks are thrown away. Okay. In Ethereum, they're kind of kept track of and they're like half rewarded. I forgot what the reward was.
Do Omer blocks have the same transaction data as?
Not necessarily. It's like we can both be mining and we can have like if we can mine, we can come up with the next block at the same time, exact same moment, and we can have different transactions included.
But the Omer blocks, like whatever data that's on it will still be picked up by the network.
It would basically, the Omer block would just be as if it never happened. Okay. It's just like orphan, but it's just being rewarded instead of just thrown away directly.
It's a Omer so you can buy the transaction. Those are just like the blocks that are still being partially rewarded right now, like the list of the Omer blocks transactions.
I don't think it's list of Omer block transactions. It's just like I think it's just a list of Omer blocks. I'm actually not sure, but you don't have to worry too much about it.
Will that still be there after the proof of stake?
Omers, okay. So orphans and Omers, they stem from, so the root cause of having orphans and Omers is that you have two miners that come to their own equally valid conclusions at nearly the same time. They're both valid, but then one's gonna outcompete the other because they're almost at the same moment or something, right? So proof of stake won't really stop it because as long as you have more than one node, one miner working at any given time. There's a chance that they come up with valid things at nearly the same time.
And it's only once they have that correct hash for the difficulty that it would become.
Well, they both have the correct hash. Both the hash both meet the difficulty. They're valid blocks.
Okay,
It's just that they happen at the same time. So then they keep building and then see who comes ahead in the next next round or whatever. And then the previous one will get discarded, and that's like an orphan or an override.
okay, gotcha,
Yeah.
thank you.
All right. Any questions? Further questions? And folks on Zoom, don't hesitate to speak up if you have questions. I cannot read chat because when you present in Keynote with Zoom screen sharing, I can't see my cursor. So I don't know what I'm pointing at. All right. We're all good. Okay, let's move on. Oh, look at that. I have my definitions. I didn't even know about them. Well, we kind of went through all of them more or less, right? Oh, look, where's my Merkle tree? I haven't asked a question. Yeah, so these are basically everything that we talked about, but to summarize into the key terms are written out here. Okay. And now let's actually click on this link. I promise you it's legit. Okay. And let me show you what a block looks like. All right. Okay. So this is actually when you're coding, whatever you get when you try to. So this is basically trying to get block number whatever 10004. Okay, so this is block number 10004. That's the difficulty. All right. Extra data. I don't know what this is. It's extra data. There's a gas limit, gas used. You can see that gas used is very little. In fact, this is the exact amount that one single Ether transfer transaction costs. Okay, 2100 units of gas. This is a block hash. This is the so now you see instead of beneficiary, it says miner. Okay, so it's a bit different. Not that it's just the wording that's different, right? Whoever coded up this software that pulls blocks decided to name it miner. Okay. And here's the nonce, and you can see that this is a huge ass number, right? Now if let me stop sharing. Like hex to decimal, okay. Let's just see what that is. Okay, so suppose our poor miners started trying from non-zero. This is how many times they've had to try before coming up with a valid hash that meets the difficulty levels. Okay. Now, I don't know about you, but that's a lot of tries, you know. So there's that. That's the nonce. This is the block number, right? Parent hash, right? The hash of the previous block. Timestamp. That's in. This is a format called seconds since Unix epoch. Is that how you say it? So basically, it's the number of seconds since January 1st, 1970, right? I don't know why it's 1970. I don't know why it's January 1st, not like December 31st, 1969. But there's that, and also list of transactions. Now, in this module that we're using, this command only gives you these data and then transaction hashes. But you can actually get full transactions by doing get block with transactions, and now you can see what goes into your transaction here. All right. So this is it. So you can see all of that. Looks kind of familiar, right? What we kind of went over. that's just to show you what things look like, all right? Okay. All right. Wow, I totally forgot I explained this here. So the three trees I talked about, right? They serve the same purpose as Merkle trees in Bitcoin, all right? They are basically Merkle trees, okay? They work the same way. So the state tree records account state, and as we saw from here, it's like the account status and everything, right? Transaction tree records transaction requests. So here's the difference. Transaction tree records the requests, and receipts records the outcomes of the transactions, and they're like one-to-one, right? For every transaction in that tree, there's one receipt in this tree. Okay, so instead of one Merkle tree, now we have three, or rather four, but three stored directly in the block, right? Four because there's also this one that's stored indirectly. Okay. So these exist. So just like how the reason why Merkle trees exist is so that clients can quickly verify things, all right? So these trees, they exist. They allow light clients, or basically light nodes, basically nodes that don't necessarily process, but it also they need to access the blockchain, allows them to easily verify. So for the transaction tree, if there's certain transactions in a particular block, now this is the exact same as the one in Bitcoin, right? Because Bitcoin is also, the Merkle tree in Bitcoin is a transaction tree, right? Now we also receipt tree, this is filtering the outcomes and event logs, all right? We don't have to worry about that for now. State tree, the current balance, if an account exists, and also, this is interesting. So what it means to dry run a contract, okay? Dry running a contract means that you pretend to call the contract, but you won't, basically you're simulating calling a contract and see what happens, but you don't actually send the transaction. It happens locally, right? It doesn't get broadcasted, all right? It's just like a simulation to see what would happen if we go through, what are the approximate effects if I do this, but I don't do it, right? It's like every time you drive on the highway or on the road, you have the urge to turn the other way and then crash into the car coming from the other side, but you don't do it. That's like an impulse, apparently a lot of people have. But you know, it's something that you pretend to do, but you don't, okay? Now, this is actually useful to, useful especially when it comes to testing stuff, because then you're able to see what happens without actually doing it to a certain extent. Okay. Any questions on the different trees here? Don't worry if you have questions. The only bad question are the ones that are not asked. Also, if you ask me what my name is, that's a bad question. Okay. All other questions are good questions. So I know the tree part might be confusing, so I want everyone to be clear. Yeah.
And so the state tree does all three things, or those three different states?
Okay. So all three things and more. This is just a few examples of what each of them can do. I probably should have formatted it differently, actually. All right, any other questions?
So it says if an account exists, it's like verifying if an account exists.
Yeah, so basically, if an account is never created, there would be no record. Okay, let's go back to the very beginning. Basically, this thing would not exist for a non-existent account. But by non-existent, I mean it's never interacted with anyone, nor has anyone sent it any money or anything, right? And when the account is not found in this data structure, then it defaults to a balance of 0 because it's like the default state, since everything is 0.
So, but what about like in those situations where like you just made an account, or like you just made an address?
Yeah.
Wouldn't it also be empty because you haven't done anything on it?
Yeah, which is why you start with no money in address, right? And the moment you make a transaction or do anything, things start happening.
Wait, what happens if you send stuff to an account that has
If you do what, sorry? If you send stuff, oh, then they'll be created.
Just create.
Yeah.
Can you re-explain the
Sure.
events and
Events.
logs thing?
Okay. Events and logs, it will be easier to explain once we start coding.
Right.
Yeah. So basically, events are what's a good way to explain? I can't come up with a good analogy for now, but you'll understand it way better when we start coding stuff and we start. Yeah. So events, it's basically a way for you to notify external parties about what happened, and you can define your own events in code. So it's all code based. So you can emit your own event when certain things are happening to let people know that, okay, this thing happened.
Okay.
Yeah.
And there's a blog that says a cheaper form of storage.
Yeah,
Is that correct?
Yeah. So yes. So the reason why events is a cheaper form of storage. So instead of, let's say, storing something inside a smart contract explicitly, you can emit it as an event. The reason being, events are inaccessible to the smart contract once you emit them. They're only visible from the outside. They're not visible from the inside.
Oh.
Meaning that I do not, like, if I'm a smart contract, I don't know how many events I have emitted. Once I emit it, I forget about it.
Is that like, so is it somewhat related to the memory thing, or is it different?
Yeah, so what memory thing?
Oh, I don't know, there's a distinguish between memory versus storage, right? With the smart contract.
Kind
So I
of.
was asking Dylan before class, but I don't know if it's.
Yeah, I think the main difference is that event information is stored in a receipt tree. But when you store something in storage, it's actually in the state tree, which
Okay,
makes it more expensive.
okay.
And also the fact that you just can't access it afterwards, and which makes sense because it's in a separate tree.
Okay,
But you just can't access it, so it's just cheaper.
okay. You
and
can access
actually-
it, but it's still there.
It's there, it's only visible from an outside perspective, but within the world of smart contracts, if you're in this code, if you are the contract, you don't know what the hell you've ever emitted.
What's a light client?
The light client is like a light node. It's a node that connects to a blockchain but doesn't necessarily do any mining or validation. Right. Any other question? I keep surprising myself with my slides because I haven't looked at it in such a long time, but they're so perfect. Okay, anyone else have any questions about this? No more questions. Actually, in our smart contract, the ones that I wrote, I use events extensively because there's so much information that needs to be on chain, but doesn't necessarily have to be accessed from within the smart contract. But I also want it to be there forever and immutable, so I use events. Okay. Transaction structure. Kind of already looked at it, didn't we? In that on that web page, but yeah, you just have, it's more or less, it's very, very similar to a Bitcoin transaction, plus the gas price, gas limit thing, and also the data part, right? Okay. So nonce, correct, double spend, right? Gas price and gas limit, we explained what they are. Well, these are all pretty self-explanatory. Oh, look, we've already looked at it, basically. Does anyone have any questions still? Let me see what's the next one. Oh, wow, I explained gas. Okay, so anyone have any questions regarding any of these? Mine is gas because that's coming up.
Oh, explain the VRS.
Okay, VRS, they're just three components. So let me actually show you something.
got. Copper pulp.
RS, it's got a no results. Wow. Signature.
Verify message. No, that's not it.
Anyhow, okay. Let me actually look it up. Stop sharing. It's sure it's somewhere here. Ah, there we go. All right. Join signature, okay? So now this is something now. Page I just. So basically, when you get a public, when you get a digital signature, it's actually able to be split into 3 parts. So just V, R, and S. That's just how cryptography works. Okay, just know that V, R, and S can be joined into a single signature string, and a single signature string can be split into V, R, and S, 3 different numbers. That's all. That's like cryptography stuff. Yeah. So there's a image. Now this is okay. This is the it's reading time. Okay. R and S. I won't read it because okay, I'll read it. R and S is the normal output of an ECESA signature, where R is computed as the x coordinate of a point R modulo the curve order n. I'm barely keeping up here. In Bitcoin, okay, it's not a trick. Yeah, basically like all this. It's the same as the mechanism in Bitcoin because they're both using ECESA.
So they're trying to randomize.
Well, not really randomized. It's just it's not randomized. It's cryptography stuff that I can't tell you. I have hit my limits. All right. You can look it up on your own, or go back to actually 256. There's this one lecture that Chaz told you to not worry about. Something about generator point G, tangents.
Yeah.
That one, yeah. Yeah, this is related to that. All right. Any other questions? No more questions. Okay, let's move on to this thing that I already talked about. Gas limit and gas price, okay? So again, limit is the max amount of transaction fee units you're willing to spend on transaction. Now, the gas limit can be more than the gas used. That's fine, okay? It's like I am 6 feet flat, okay? It is okay for me to buy a door that's 7 feet tall, okay? But it is not okay for me to buy a door that's 4 feet tall because I can't walk through it, okay? So for gas limit, it's okay if you're saying, okay, I'm willing to spend more than what I actually spent, but basically the difference won't be charged, it'll all be refunded, okay? But you cannot say that I'm not willing to spend as much just because I'm cheap. That way, because again, the gas used is based on computation and storage, so you can't change that. And what happens is that if you're not willing to pay that, then the transaction's not gonna happen.
For gas limits, why wouldn't it just be the limit every time? Why would it ever be less than what the gas limit is? Because what if miners want to, if it looks to take that, what if they want to get that?
Sorry, can you repeat that?
So why is it that sometimes there's like, if someone sets a gas limit, whatever, the actual gas usage is lower, why is that?
Okay, so let's say you're interacting with let's say your interaction involves your transaction, your transaction being routed through like 2 or 3 different contracts. So sometimes you cannot correctly or accurately estimate the amount of gas that some other contract will use, because sometimes you don't have your source code or whatever, right? Sometimes the estimate is just off, maybe it's different based on the logic, because we said there's like, if this, if not, whatever, what if it goes into it, what if it doesn't? Sometimes it's not completely accurate, which is why you want to set it to be higher so that it doesn't fail, because it's not gonna charge you for the full amount anyways. But you're saying I'm allowing that much to happen. So that's why sometimes the actual amount is a bit lower than the limit.
What's the unit for gas? Is it just like, is it a price or is it a?
So the gas limit, it's just, there's no unit, it's not a price. The gas price is the price. Okay, so the gas limits unit is gas, I guess, like there's no unit. The gas price, that unit is price per unit of gas. Yeah. So the price is however you're willing to pay per unit of gas. And that's determined by the market. Yeah. So again, it's just like Bitcoin, it's a bidding thing, right? If you want to get your transaction through faster, then outbid the other people.
So if you make your gas limit higher, that's your outbid.
No, gas price higher.
Okay.
Yeah. So transaction fee equals gas used times gas price. Gas used is always less than or equal to the gas limit.
I've heard of like G-Way being used when you talk about gas.
Oh, that's right. Oh, I totally forgot. That's the unit. I totally forgot. I'm sorry. Did I talk about it? Oh, I don't. Surprise myself. Yes, it's G-Way. Yes, you're right. It's GWEI. I don't even know how you're supposed to pronounce it. Is it just G-Way? I don't know. Way, G-Way. Way.
G-Way.
G-what?
G-Way.
G. I don't know. Wait.
It's GWEI.
Yeah.
Okay. GETH is something else. It's the Ethereum client written in the Go language. It's the official implementation of the Ethereum client. So that's like GETH. Sometimes you see it.
Yeah. Right.
Yeah. Go is an actual language made by Google. Yet another programming language. All right. Any questions on this part? This is important. Okay. Although, again, your test will just be coding stuff, but this is very important. Any questions? Now, this, we're not going to look into it because it will just confuse everyone. So you can click into the link and read through it yourself. But basically, it's being split, the gas fee is being restructured into something called like a base fee and then something else I forgot. But this is still like still important to know. Okay. Right. Any questions on this part? Is this clear, everyone? How transaction fees work in Ethereum? It's a bit more complicated than the Bitcoin stuff because in Bitcoin, all you could do more or less is send money, and there's no other way of interacting with anything. So the fees are the amount of computational power used is more or less the same. Right? Like Ethereum, you can do crazy stuff like lose your money through some DeFi protocol. So so there's more involved in that. No questions. Let's move on. Ethereum applications. Ethereum first. No. Decentralized finance, right? AKA the fastest way to blow through all your savings. Uniswap, SushiSwap, etc. They're basically decentralized exchanges. Now, this is pretty interesting because for those of you who who here has some kind of exchange account, have used an exchange, Coinbase, Kraken, FTX, whatever. Okay. Who here has used some DeFi swap thing? Okay. So in the regular exchange, they do like an order book system, right? Basically price matching with a certain slippage that the exchange earns as part of how they earn money, right? But the thing is, if you noticed, actually, should I show it here? No. Let me show it actually, show it briefly. Okay, let me show it on my phone actually. So basically, in an order book system, okay, everything happens very, very quickly, right? The faster it happens, the more throughput the exchange can handle, meaning the more transaction fees they can collect. Okay? And now this is different from the blockchain transaction fee. This is strictly when you're buying stuff from them, they charge you a fee just because they can. Okay, so let's take a look at the Bitcoin USD pair. I don't know if everyone can see it, but you can see that this thing is changing all the time. That's orders being matched up and fulfilled all the time. Now, obviously, this is not possible on Ethereum. Why? Because the single action takes 10 seconds to confirm, right? You can't have that. You can't, like, you don't see, like, these are moving hundreds, thousands, tens of thousands of times every single second, okay? You can't have that. You can't have an order book system on chain. That's just not gonna work. So instead, they came up with something called, I think, is it Automated Market Maker, AMM, okay? I am not going to go into how that works because it's not a part of anything really this course. But it's something fascinating that you can, go and do some research yourself how that works. Okay, they basically solved the problem of how do I match people up without having an order book system. Okay. And also supply chain management. Why is it important? Because why is it good on Ethereum? Because or not just Ethereum but blockchain, because everything's immutable, everything's transparent, right? There's a clear paper trail everywhere because it's just all on chain, right? Decentralized identity, right? That's just like your MetaMask or ENS, right? Ethereum name service. Who here has an ENS thing? Okay. All right. Who wants to explain what an ENS is?
Oh, it's like shortening like your 64 hex name into like a .eth. It's like you can send the Ethereum or any ERC20 token to like Joey Reinberg.eth instead of
nice
wallet.
Is that like the unstoppable domain?
It's similar. It's a different system, but it's similar. Yeah.
It's also like an NFT. It's like you can trade it too.
Yeah. Yes. Yeah. So that's one part of the decentralized identity, right? Also, decentralized and immutable storage of information, right? Now, people do that all the time using. Like sometimes they leave notes or whatever in the transactions or blocks or like RV was basically a blockchain that's designed to store data. So storing data up there is pretty cheap. So whatever data we store up there will be forever immutable as long as the RV blockchain exists, right? Also, DAOs, decentralized autonomous organizations. Jeff, I feel like you're into this, right? Yeah. Yeah. Do you want to tell people what it is?
It's basically kind of like an organization that's built around membership tokens, and people get to vote on what to do with the money on their account. And by having a token that you can record like who votes what, and then that clarifies a lot of things that centralized organizations can't.
Yeah. So this is basically like buying company shares and voting on company decisions. Only this process happens ideally completely in a decentralized way, and there's no central figure that can veto or do anything about it. Like people can propose it, and it'll go through like a process of voting we should keep proceeding with this idea and then eventually move on to like a formal voting process, right? But ideally, no one can veto it, although in most DAOs, that's not the case. Most DAOs are fake DAOs, okay? They're not DAOs, they're CAOs, okay? And yes, I know why you're laughing. And more, okay? And that's it for today. Perfect timing. Yeah, you have a question?
Yeah, one of the questions on the homework asked about ERC-20
What do I say about that? Let's see.
they're different from ERC.
I talked about it. I talked about it when I was talking about wrapped ETH.
It says list 3 uses that are not shown in the slides. What are what's the slide for that?
Oh, that's right. Oh, where did the slides go? Okay, I'll take that out. I took that out.
Just the list 3 question.
Also, one more thing. Okay, so if you go to the homework stuff, this one, 7, we know smart contracts can delete themselves via the self-destruct opcode, but are they completely scrubbed from existence? Why or why not? Okay, so in smart contracts, there is an opcode called self-destruct. What it would do is it would basically, I don't have to explain what self-destruct does. It would just make the contract unusable, uninteractable. Basically, no one can ever use it again. It's basically deleting itself. But are they completely scrubbed from existence? Can you completely delete something on Ethereum from existence? Why or why not? So basically, explain that. So the question is basically, can you delete something from Ethereum completely? Why or why not? Okay, and also these, please, guys. You know, there are 3 points, but please answer them. And please don't lie to me, okay, because I will know. But aside from that, if you have any questions, post on Piazza. Aside from that, I said that twice. That's it for today. Thanks for coming. I'll see you on Thursday.